and welcome to the fifth and final section of our unit on circuits and DC instruments. In this unit, we're going to do some examples involving Kirchoff's rules. Really, what it is one example that I'm going to work twice to help illustrate the sign conventions for the voltage rule, and also to help you see how you can make different choices and get the same answer. Okay, so here is the circuit that we are going to analyze. We can see immediately that this is not a circuit we can do equivalent resistance on, because we do have two resistors, a 6 volt, flip that. We have two batteries, a 6 volt and a 3 volt. We have let me count again. We have 5 resistors on this guy. Okay, so step 1 is to choose the directions for your currents. I am going to choose to think about my 6 volt battery, and therefore I'm going to let I1 go through the 6 volt battery from the negative to the positive, because it's the biggest thing in the circuit and it seems like it should dominate. Okay. Now you might expect the 3 volt to, help the 6 volt out. They are pointed in the same direction, but I am going to just blindly choose I2 going to the right, and I'm going to let I3 come up the middle. So what does this mean? It means that I1 flows through the 6 volt battery, through the 12 ohm resistor, through the 8 ohm resistor. At this junction, if I go up, I switch to I3. If I keep going straight, I'm now into I2. And I2 will go through the 10 ohm, the 3 volt, and the 2 ohm, obviously in the other direction based on my arrows. If I look at this junction, I have I3 coming into the junction. I have I1 and I2 leaving it. So my junction rule gives me that I3 equals I1 plus I2. Okay. I have 2 branches for this circuit, therefore I need to choose 2 loops. I'm going to choose, again, to color code my loops just to help you follow along a little bit. The first loop I'm going to choose is this one. Okay. If I look at that loop, and again, remember, I like to start and stop at batteries. So I'm going to start at the 6 volt battery. My loop goes through the 6 volt battery from the negative end to the positive end. Therefore, for my loop rule, I add in 6 volts. I then follow I1 around. It goes through the 12 ohm. It goes through the 8 ohm, both of those following the current. So I subtract I1 times 12 ohms. I subtract off I1 times 8 ohms. I hit the second junction. This loop is only in the left-hand side of the circuit, so I'm going to turn and go up. And my loop and I3 are in the same direction as I go through the 6 ohm. So that's minus I3 times 6 ohms. That will bring you back to this upper junction. I'm going to turn, head back to my battery, which is where I started, so I'm going to let that equal 0. I can now simplify this. I have an I1 times 12 ohm and an I1 times 8 ohm. That is going to be 20 ohms I1 minus 6 ohms I3 equals 0. Okay, now for the next loop. Oh, let's go blue. I'm going to choose this loop to go like this. Now, why did I choose that direction for this loop? Because this way I'm always moving in the same directions as the currents that I chose. Makes it a little bit easier from the sign convention standpoint. Again, I like to start and stop at batteries, so I'm going to start and stop at the 3 volt battery. So my loop is coming around. I hit the positive terminal of the 3 volt battery first and then the negative. So on this loop, I'm going to subtract off 3 volts. I'm going to follow the 10 ohm follow the current through the 10 ohm resistor. So I'm going to subtract off 10 ohms I2. hit the lower junction, turn up, and go through the 6 ohm resistor in the same direction as I3. So minus 6 ohms I3. Remember, this is IR. So, and multiplication is commutative in that 2 times 3 equals 3 times 2. So it doesn't matter if I write 6 ohms times I3 or if I write I3 times 6 ohms. They're equivalent. Okay, back to the circuit. I went through the 6 ohm resistor, hit the upper junction. I'm going to follow I2 through the 2 ohm resistor. So I'm going to subtract off that. And that will bring me back to my battery. So I let it equal 0. And I'm again going to choose to simplify this equation by combining the two I2 terms. Okay, we now have a bit of algebra to do. The way I like to do this algebra is I like to leave for myself almost a trail of breadcrumbs to follow, so that if I make a mistake while doing the math, I can see what I was trying to do at each step. For my trail of breadcrumbs, what I do is I name my equations. A, B, and C. I'm a creative namer. What can I say? Okay. Now what I have to do is think about a way to solve these simultaneously. I need to know what is I1, I2, and I3. Okay. So when I do this, what I look at and see is that I have equation B, which is in I1 and I3, and equation C, which is in I2 and I3. I can use equation A to rewrite B in terms of I2 and I3. Once I have B in terms of I2 and I3, then I can use B and C together, or the new B, if you will, and C together in order to solve for one of those two. Okay. Remember, when you're solving simultaneous equations, what you're trying to do is eliminate a variable. So the first step I'm going to do is get rid of I1 from my equations. Okay, so step 1. Step 1 is solve A, and that's going to create D, or rearrange A is a better word. Okay, so when I do this, I always begin by writing down what is my starting equation. Equation A is I3 equals I1 plus I2. Now, as I just discussed, what I want to do is rearrange this, solving for I1. So I1 is going to equal I3 minus I2. And this new equation is the one that I'm going to call D. For step 2, I'm going to take my new equation D, plug it into equation B, and that's going to produce an equation which I will name E. Okay, so I'm taking D and plugging it into B. So the first thing I need to do is start with equation B. 6 volts minus 20 ohms I1 minus 6 ohms I3 equals 0. Now I'm going to take D and plug it in. So 6 volts minus 20 ohms times I3 minus I2 minus 6 ohms I3 equals 0. So simplify. Minus 20 ohms I3. I have a negative here and a negative there, so that combines to be a positive 20 ohms I2 minus 6 ohms I3 equals 0. And now I'm going to collect like terms. So 6 volts minus 26 ohms I3 plus 20 ohms I2 equals 0. And that is my equation E. Okay, so now I know the next thing I'm going to do is somehow combine E and B to try to eliminate one of the two remaining currents, I2 and I3. The way I'm going to choose to do this is to do the substitution method. For the substitution method, what I want to do is take one of my two equations, solve it for one of the variables, and then plug it into the other. So for step 3, I'm going to rearrange E, and that's going to result in the equation I'm going to call F. And I'm going to rearrange E such that I solve for I2. Okay, so again, starting by writing down my starting point. That's my equation E. Now I want to solve for I2. So the first thing I'm going to do is move everything else to the other side of the equation. Okay. And now I divide by 20 ohms. So I2 equals negative 6 volts plus 26 ohms I3, all divided by 20 ohms. Okay, and this is equation F. Okay, step 4. I'm going to plug F into C, the equation from the beginning that I haven't used yet, and that's going to allow me to solve for I3. Okay, so begin by writing down equation C, minus 3 volts, minus 12 ohms I2, minus 6 ohms I3 equals 0. Now I'm going to plug F into this. So minus 3 volts minus 12 ohms times equation F, which was 26 ohms times I3 minus 6 volts, all divided by 20 ohms. And I may have written the terms in the numerator in the opposite order, but they're the same signs, they're just flipped around. Minus 6 ohms I3 equals 0. Now I have to distribute through my parentheses. So I have a term that's 12 ohms times 26 ohms times I3 divided by 20. And if you want to write that all out, you can. But at this point, I'm going to advise that you get a calculator. That works out to be negative 15.6 ohms times I3. We also have another term that is negative 12 ohms times negative 6 volts divided by 20. Negative times a negative will give us a positive number. The ohms, units of ohms will cancel, and that leaves us with plus 3.6 volts. That takes care of the parentheses. I have a minus 6 ohms I3 that I need to bring along, and now I can solve for I3. First thing I want to do is collect like terms. I have a negative 3 volts and a positive 3.6, so that's 0.6 volts. I have negative 15.6 ohms I3 and negative 6 ohms I3, which works out to be negative 21.6 ohms I3 equals 0. And I can now write that I3 is going to be 0.6 volts divided by 21.6 ohms, which works out to be 0.028 amps. Done. It's a lot of algebra, but it's successful. Okay, step 5. Step 5 is to take I3 and plug it into F. And that's going to give us a value for I2. So remember, F was that I2 equaled 26 ohms I3 minus 6 volts over 20 ohms. So that's 26 ohms times 0.028 amps minus 6 volts divided by 20 ohms, and that works out to be a negative 0.264 amps. So I'm just going to make a little note here. This was I3, this is I2, which brings us to our final answer, our final step. Step 6 is put I3 and I2 back into, wrong arrow, that should be this arrow, into equation D, and that will result in us knowing I1. Equation D said I1 equals I3 minus I2, and that is 0.028 amps minus a negative 0.264 amps, which works out to be 0.292 amps. Done. Okay, now let's take our answers and go back to our original circuit way back here. We found that I1 equaled 0.292 amps. Okay, that means it's positive. The direction that we originally chose for I1 is correct. We found I3 equal to 0.028 amps. It's positive. The direction for I3 that we chose is correct. I2 we found equal to negative 0.264 amps. And we see that this number is negative, which means I2 doesn't go the way that we chose. It actually goes the opposite direction. So as we kind of expected and then chose backward anyway, the current is going to go through the 6 volt, around through the 12 ohm, through the 8 ohm. At this junction, it's going to switch from I1 to I2, and I2 actually will flow up through the 10, properly through the 3 volt, or from negative to positive through the 3 volt, through the 2 ohm, in the opposite direction of the red arrow. Okay, so that was one way through the math, one way through the algebra. So let's do this particular problem again. And we're going to make different choices this time. So switching back to red, step 1, choose the directions of your currents. So I'm going to choose what I probably should have chosen the first time in looking at the circuit, but then purposefully chose backward. Okay. This gives me I1 is heading away from this junction, but I2 and I3 are both heading into it. So the junction rule says that I1 equals I2 plus I3. Remember, that's the one that says current in equals current out. Okay. I'm now going to choose my loops. The first loop I'm going to choose is the exact same one that I chose for the first version of this. Starting at the battery, I get 6 volts. I'm going to take I1 through the 12 ohm and through the 8 ohm, following the current. Therefore, I can subtract off 20 ohms times I1. And then I'm going to head up through the 6 ohm following I3, so I subtract that off as well. For my second loop, in this case, I'm going to choose to go around the outside. Okay, so that's 6 volts, starting again at this battery, minus 20 ohms I1 through the 12, through the 8. At the junction, I switch from I1 to I2, but I'm going in the direction of I2. Right? Okay, so I2, I go through the 10 ohm, so I'm going to subtract off that, minus 10 ohm I2. I hit the 3 volt battery. I go from the negative edge to the positive edge, so I actually add 3 volts in. And then I follow I2 through the 2 ohm resistor. So minus 2 ohms, I2 equals 0. Now I can combine like terms here. So that's 9 volts minus 20 ohms, I1 minus 12 ohms, I2 equals 0. Okay, and just like before, I'm going to leave myself a trail of breadcrumbs. So I'm going to label my my functions or my equations, and to be consistent with my notes, this is actually equation C and this one is B. Okay, same idea as last time. The goal is to solve these 3 equations simultaneously, and I want to begin by removing one variable from my equations. I look and I see C is in I1 and I3, whereas B is in I1 and I2. So what I'm going to do is I'm going to take A, solve it for I2, and plug it into B to remove I2 from that equation. As my first step is going to be to rearrange equation A, and that's going to result in equation D. So equation A says that I1 equals I2 plus I3. As I just discussed, I want to solve this for I2. So I2 will equal I1 minus I3, and that is equation D. Step 2. For step 2, I'm going to take equation D and plug it into B, and that's going to result in equation E. So equation B is 9 volts minus 20 ohms I1 minus 12 ohms I2 equals 0. So 9 volts minus 20 ohms I1 minus 12 ohms times I1 minus I3 equals 0. And now I need to remove the parentheses. And combine like terms. So 9 volts minus 32 ohms I1 plus 12 ohms I3 equals 0. And this is my equation E. Now, what I'm going to do is I'm going to take and write down again equation C, because I want to look at it and compare it to E. C said 6 volts minus 20 ohms I1 minus 6 ohms I3 equals 0. And I'm going to look at those two, and the thing that I am focusing on is this term. Look at that. Plus 12 ohms I3 minus 6 ohms I3. I can do something with that. But it would be much more helpful if that 6 were a 12. Okay. So what am I going to do? For step 3, oh, I circled the 3 there. Not sure why. Okay, for step 3, I'm going to take equation C and multiply it by 2. Why am I multiplying it by 2? Because I want that 6 to be a 12. Remember, I can do anything to an equation as long as I do it to every term, right? So a 2 overall isn't going to make a difference. I'm then going to add that equation to equation E. And when I add those two equations, now I'm going to have a plus 12 and a minus 12 on the I3 term, which is going to allow me to immediately solve for I1. Okay, so first step is take 2 and multiply it by 6 volts minus 20 ohms I1 minus 6 ohms I3 equals 0. That results in 12 volts minus 40 ohms I1 minus 12 ohms I3 equals 0. And now I'm going to add to this equation, so plus equation E, which was 9 volts minus 32 ohms I1 plus 12 ohms I3 equals 0. Okay, 12 plus 9 is 21. 40 plus 32 is 72, but that was overall negative, so you get minus 72 ohms I1. And then I have minus 12 ohms I3 plus 12 ohms I3. Those go away. They cancel. And now I can solve for I1. I1 equals 21 volts divided by 72 ohms, which is 0.292 amps. Okay, we have I1. This is fantastic. Step 4. For step 4, I now want to find I3. So to find I3, I'm going to take I1 and plug it into either C or E, but in this case I chose E, and that will allow me, I may have said I2, I meant I3. That will allow me to find I3. So 9 volts minus 32 ohms I1 plus 12 ohms I3 equals 0. So 9 volts minus 32 ohms times 0.292 amps plus 12 ohms I3 equals 0. 9 volts minus 32 times 0.292 works out to be 0.33, a negative 0.33. So I get negative 0.33 volts plus 12 ohms I3 equals 0, which means I3 is going to equal 0.33 volts divided by 12 ohms, which is 0.028 amps. And we have I3. For the last step to this process, step 5, I'm going to take I1 and I3, plug them into equation, that should have been this arrow, equation D, and that will result in me knowing I2. Equation D says that I2 equals I1 minus I3. So that's 0.292 amps minus 0.028 amps, which is 0.264 amps. And I have, at this point, worked the same circuit twice, making different choices on the directions of my currents, how I do the algebra, the directions of the loops, which loops I choose. And because I was self-consistent every time I worked this, I got the same answer both times. I hope you found this helpful. And in the next unit, we will be investigating magnetic field and magnetic force.